artificial Anasazi case study, a segregation model built by Eris, and some findings we have there, and also on a social media, online social media model that we built at the lab. So social systems produce a lot of correlations and distributions at both the micro and macro levels. And in recent years, predictive algorithms have become more and more effective at being able to predict outcomes into the future. However, the fact is that these systems are complex, they are nonlinear, they produce emergent phenomena, and they're highly sensitive to small perturbations. So the fact is that the explanations of these systems lie in the generative individual scale mechanisms that lead to these emergent phenomena, as we've been discussing throughout this workshop. So the individual scale mechanisms of these systems cause these individuals or agents to interact, and the whole systems follow this trajectory through the state space. And as we all agree, I believe, agent-based models are great at capturing this movement through the state space, and at the same time, they're able to do this while embedding human interpretable rules at the agent level. So when we go about creating an agent-based model, we first start with some theories or concepts, and hopefully merge this with some data, and we come up with hypothesized individual scale generative mechanisms, which we then embed within our agent's brains. We could use different cognitive frameworks, such as Agent Zero, which Josh introduced. And after we run our simulations, we can validate this output against data. Now, we can go a step further and calibrate our agent-based model to the data so that the outputs seem more realistic. But the fact of the matter is that the generative mechanisms stay the same. So the submodels stay the same. You could parameterize your rules. However, the underlying structure of the equations, the utility functions, or the decision trees typically don't change that much. So the question we're trying to answer is, how can we infer explanations of societal phenomena at the individual scale while respecting the fact that the systems we're trying to model are complex, and they have all these emergent properties, they follow nonlinear trajectories, and they're highly sensitive to perturbations. And at the same time, ensure that we're providing explanations that are human interpretable so that we're making a meaningful contribution to science. So the evolutionary model discovery aims to help with this process, and it combines agent-based models with genetic programming and random forest to try and achieve this. So this is an architecture of what evolutionary model discovery actually does. So first, on the left-hand side, we need an agent-based model, of course. It will not spin up agent-based models out of nowhere. But what we need to do, given an agent-based model, is we need to identify a particular rule, a submodel, and a rule which we are unsure about, which we want to explore. And unlike a calibration, we do a white box evaluation analysis of this particular rule. And in order to do that, we need to provide units of causality, so small explainable units that we can interpret, that we believe come together and drive the behavior that we are trying to study. And then evolutionary model discovery will basically genetically program that particular rule, inserting in these factors of decision making that we've provided. And it'll do this optimization by evaluating the performance of the simulations against macro patterns in data that we find to be interesting or we target for. So the output of this optimization process will then be these behaviors, alternate behavior rules, which are, each of these agent-based models that are evolved along the way represent sort of an alternate universe where agents are doing different things. And at the end, we get this whole compendium of alternate agent behavior rules and how much fitness they provided us with. Now, instead of stopping here and trying to say that we found the optimal solution, we go a step further and we train a random forest regressor on the produced data. We train the random forest regressor on the presence of each factor to the fitness that we see from the agent-based model at a macro level. And the reason we do this is because random forests are great at assessing the importance of factors that are in the training set. So we use random forest factor importance assessment to then tell us which factors actually contribute more towards fitness. So now that we have an idea of the more important factors, we can go ahead and identify their optimal factor presence. So through this optimization process, we're exploring the fitter portion of the factor space. And then we're using random forest regression to understand which factors are more important when trying to get to that portion of the landscape. And then we try to find their optimal presence. So we define causal factors in our implementation simply as primitives in the genetic program. So they take in commands. They require some information in order to function, which could be the state of the neighbors or the environment, and they return some information which then gets aggregated into a subutility or a decision. Hopefully these factors encode some sort of human interpretable unit that can help in our explanation of the overall behavior. And these factors have to be strongly typed so that they can combine with the relevant operators. So together, these factors will combine and form a factor tree. And this particular factor tree, its conceptual factor tree, is inspired by both Agent Zero and some of Paul's work. So just like Agent Zero, on the right-hand side, we have a combination of, a deeper combination actually of multiple theory components, which include social, emotional, and rational components, depending on the problem at hand. And they basically help us select from a set of possible behaviors, which are interpreted through a particular social network configuration. So the social network configuration in this particular structure sort of acts like an ADF in genetic programming. So the reason we use genetic programming is because it's great at manipulating functions. It's great at restructuring functions. So as you can see, using the crossover and mutation operators, we're able to completely convert functions. Like we can go from a minus 2bc to 2bc plus ba. And on the other example, we can go from c squared plus ba, take out the interaction term, and add in plus a minus b. So we're basically changing the fitness landscape instead of trying to explore points along a particular plane that this function might, that one function might describe. So that way we could explore certain points in the factor space that might contain the solutions that we want. So these genetic programming syntax trees are really useful in terms of providing us with a grammar, which we can then both interpret at the end for our benefit when trying to explain why certain decision trees, syntax trees, were stronger than others. And we can also easily recode these into NetLogo or repass or whatever agent-based modeling framework we're working with. And finally, we use two different types of factor importance analysis techniques, Gini importance and permutation accuracy importance, which basically try to tell us, given different factor presence values as an input variable, what is the importance of those factors towards the reprediction of the fitness that was generated through the genetic programming process. And in my experience, what I found is that the permutation accuracy importance was superior to the Gini importance, which also reflects in the literature. So going on to some implementation details, I started this out with ECJ and tried a little bit of F-cube, but I found that implementing the genetic program in Deep was quite flexible. So that's what's in the implementation at the moment. Deep is also parallelizable, so that helped. For random forests, I use the scikit-learn library and several other libraries that are available in Python for the permutation accuracy importance and also joint contribution. And as it is, the evolution model discovery software works on NetLogo. And since these problems require a vast exploration of the search space, obviously everything is parallelized. Everything runs on the cloud on AWS. And the evolution model discovery software is open source. It's available online. It's QR code and some source code in the presentation. I've tried to make it as easy to use as possible. So all you have to actually do, you have to just do two things, basically. You need to, in the first diagram, you can see a comment that says, @EMD evolve next line. So basically, you tag the particular line of NetLogo code that you want to evolve or explore. And then you can specify an NLS file, or you can have your factors in the same script. The second blurb there basically shows you an example of a factor, and then you basically annotate that NetLogo reporter with @EMD factor, and then add in the return type and the parameters that you need, and the plugin, the Python package just picks all that up and does the genetic programming for you. So you just have to code in NetLogo. And it requires a little bit of Python programming to start. So you set up some parameters, and you say what you want to measure, how many ticks you want to run for, and you simply say, you have to provide an objective function, and then you simply say EMD evolve, and the genetic programming starts. So Deep, under all of this, the Deep library is running the evolutionary process. This also has resulted in creating a Python package for importing NetLogo into Python, so that's available here too. So let me run quickly through three of the case studies that we studied. So the first is understanding the socio-agricultural behavior of the ancestral pueblo. So we do this looking at the artificial Anasazi model. Two of the creators of the model are actually here, Rob and Josh. And this model actually looks at trying to explain the sudden demise of the ancestral pueblo towards 1300 AD. And the objective of this model is to try to follow this population curve of households. And an interesting submodel that the artificial Anasazi has is that as a particular household grows, it can deplete its farm plot. And when that happens, it tries to go in search of a new farm plot. Now, the farm plots around it could be occupied, and there could be water in the area. So there's a set of potential farm plots that it can move on to. And then it chooses the closest one. So we decided that that's probably not that rational. If your current farm plot failed, you might want to go further out, find higher quality land, or you might want to move towards where everyone else is moving, so social presence may be at play. So the original model looks at full information. We also looked at a social network where agents are only considering the best performers on the landscape. We also considered a social network where agents are just listening to their family agents, or where the households are getting information from their nearest neighbors. So we considered these four social networks for the information inflow. And then for factors explaining why they would select a particular farm plot, we considered quality of the soil, dryness, yield, the water availability, distance, homophily, social presence around the next neighborhood they want to move to, and whether they want to actually migrate out from the zone they're in. Now, all of the data required to run these factors were actually in the model, so you didn't have to build anything in. So the original model looks something like this. So basically, take the full information of the valley and select the farm plot, which is argmax, so the closest, so argmax and minus distance, the closest farm plot that's possible to you. And the results from the genetic program were quite different. We repeatedly got some better performing trees, and we repeatedly got trees which had comparison of quality, for example, and comparison of positive distance. So these are some examples of the simplified equations of the trees, and we find that many of them, all of these that are shown for you actually are better than the calibrated original model. We find that the social network configurations, when you compare them, we find that full information actually is the best social network configuration out of the 4. And when we do a statistical test on them, and we find that, so looking at the factor importance results provided by the random forest, we find that the fitness is best predicted by quality of soil, then social presence, then distance, and then migration out of the zone, and other factors are less. So this was quite interesting to us. I actually ran this experiment several times in different settings to kind of try to see if this was just a coincidence. But so what you see here is a Mann-Whitney U-test of each factor, each important factor that we saw in the previous slide at presence A versus presence B. So if it's green, it's past the Mann-Whitney U-test. So what we see is that quality, which was the most important factor, is actually better when present positively. Social presence is also better when present positively. Migration was better when present positively. Dryness was kind of disputed there because it was interacting with some of the other factors, but again, it had sort of a negative effect. And distance was better when present positively, not negatively as in the original model. And when we use these insights to build our own farm selection strategies and compare them against the original model, we find that these farm selection strategies that we come up with are far more robust than the original model. So here we're comparing all of these models with random parameter initialization. And we find that the models that compare quality and social presence or migration perform better than the one that just tries to minimize distance. So the insights that we gain here are that the farm selection strategy of the Anasazi was probably more intelligent, and the ancestral Pueblo probably tried to look for higher quality soil and had an affiliation to each other, so considered soil presence, social presence, and they probably tried to move further from the farm plot that that had currently failed. So the second case study looked at the segregation model, and as you all know, the Schelling segregation model tries to show to us how even a small tendency to want to be next to someone who is of similar race, live next to people of similar race, could lead to highly segregated neighborhoods. And this is a product of the nonlinearity of complex systems. And Ayres, in his work, has gone ahead and extended this model. And according to his observations, it's more likely to find mixed patterns of segregation and integration in actual urban environments. And he's extended some of the segregation model's rules. So agents are now able to compare the utility of their current residents versus all the other residences they want to move to, and then decide whether they want to move or not. And also when they're completely satisfied, there's a noise factor where they could still want to move. So given Ayres's model, I tried to explore the different factors which could lead to the wanting to move to a particular household. So what the utility of the next neighborhood that they want to go to. And this utility function is also the function that they consider their current residence with. So the different factors that we explore here are the original factor, of course, the fraction of racially similar households, the average tolerance of the individuals in that neighborhood, the diversity of tolerance in that neighborhood, the isolation provided by that location, so the negative of the inverse of the crowding factor, the length of residence at that particular location, sort of a stickiness factor, and the average satisfaction of that neighborhood, the diversity of satisfaction of that neighborhood, the distance from the current location, and the tendency, the historical tendency of that agent to move. Here we're measuring the C index, which Ayres has developed to measure mixed patterns, the presence of mixed patterns. So when the C index is higher, we see more and more mixing of integrated and segregated patterns. And some of the results from the genetic program, in this case, are actually quite similar to each other. So we see race coming up, we see a negative move, so lack of the inverse of the tendency to move coming up. And we see the need for isolation coming up. And all of these provided reasonably high C index values. And looking at the random forest results, we find that move, race, and isolation, need for isolation, are the most important factors. And their optimal presence, move has a negative impact on utility. Models with negative move have a better utility, a better fitness. And race is best considered positively. So when people want to move towards racially similar areas, then these mixed patterns are more likely to come up. Isolation is positively favored. And these diversity factors that we had in are sort of debated because they were in interaction with the other factors. And what we see is that when we include race, negative move, and isolation, we get far higher C indices than when we have the original factor, which is just consider race. And actually, one of the interesting things is how these factors have to interact in order to get these mixed patterns. So when we have just simply move, we get these very, I call them random. Josh, you called it something else the other day. But we get these very random sort of patterns. And need for isolation alone also provides you the same results. But when we combine these two factors within the rule, we get these pockets of isolation. When people are have a lower tendency to move, and however, when they favor isolation. And as you know,
I remember what it was. It wasn't that they're not exactly random. They don't like to be together.
They don't like to be together, yeah.
I was reminded of this famous aerial photograph of spring in Bryant Park, where everybody's blanket is equally spaced. And I think because it means people don't really want to be together.
Yeah.
Not exactly.
That was it. Yeah. So as you all know, the original factor, the racial similarity, gives us these segregated patterns, completely segregated patterns. But then when we combine all three factors together, we very easily get these mixed patterns. So that was pretty exciting. So none of these factors alone, or even couples, could give us these mixed patterns over a wide range of the density parameter. So the insights are that racial bias by itself is insufficient, and it's actually that interplay between racial bias, avoidance of crowding, and tendency to not move that easily provide us mixed patterns. So I'll go through this case very quickly because I think I may be running out of time. But here we're looking at factors that drive prioritization of responses. under information overload on online social media. So in collaboration with Bill and Ivan, we've come up with, and Nisha, we've come up with information theoretic agent-based model of conversation. So here we're basically building up this stochastic network of action where users act on conditional probabilities. And the way we measure these conditional probabilities is by taking a ratio of their marginal transfer entropy over their entropy. So it's basically how much of the information that flows out of myself is coming, of information that flows through my neighbors. And we do this for every single dyad that's in the network, and we build this network of conditional probabilities. And on top of this network of conditional probabilities, we have agents which have an extended working memory, we call. So since their social media selves are sort of an extended self of them, we use the theory of extended self from social sciences and combine that with working memory theory, which is in the cognitive sciences, and we come up with this theory of extended working memory. And very simply, without going into too much detail, how this all works is we have this actionable information queue. And initially, this queue has a certain length, maximal length, Mmax, which is our working memory capacity. And when we receive more information than we can process, then this actionable information queue is subjected to stress, and we have a message overflow. And then we recalculate what this new memory capacity would be, and because users undergo a certain amount of attention loss when they are subjected to information overflow. And we end up dropping out messages, and what we've seen through analytical studies is that the resulting new memory depth, or the new Mmax, the new working memory capacity is now smaller. So the thing we want to explore here is, once we've done that and we've dropped the other messages, do these messages still stay in order, or do they reorder themselves in terms of a certain priority? So we try to calculate this particular priority, and evolutionary model discovery was used to explore a bunch of factors that we hypothesized affect the prioritization of response when a user is under information overload. So we considered recency, the popularity of the conversation being sent to you, the popularity of the user who initiated that conversation, the size of the conversation, the common interest seen between the user who's sending the information to you and yourself, the reciprocity, the historical tendency of you to respond to that particular user, the popularity of any URLs or content within that message, and the familiarity, the historical familiarity of you, of yourself to any information within those messages, and your expertise on that information being discussed. And all of this was calculated on CUDA GPU using a Python number, because we considered many users from the social sim data set that we received. And we looked at the 8 most active Twitter profiles, but we searched over maybe like 1 billion relationships that these users could have potentially had with others, and we toned it down into the few hundred relationships that we actually saw influence from. And all of this was so that we could gain knowledge on the prioritization behavior and then transfer it to this at-scale model, which we had in GPU with 10 to the 7 relationships and simulating a year of activity. And we're trying to reduce the root mean squared error of responsiveness seen in the actual data and produced by the simulation. So what we see is even simpler behaviors than we saw in the previous case. We see recency coming up a lot, and we see the conversation initiator's popularity coming up a lot, and reciprocity, for example. And since we included more operators in this study, we had multiplication division, we get a lot of factor interactions. But looking at the top ones, we see that recency is by far the most important factor, which is reflective of the literature. There's literature confirming this result. And the conversation initiator's popularity and the interaction of the conversation initiator's popularity to recency as well, followed by the interest to the content that's held within the message received, and conversation size, conversation popularity as we go down. So analyzing the factor importance results, we find recency, conversation initiator's popularity, conversation size, URL popularity, the interest to the content of that message, and user reciprocity as the more important factors. And we find that recency's optimal presence is positive when conversation is started by users who are less popular globally. Users are more likely to prioritize response. When conversation size is smaller, users are more likely to respond. And when the common interests are less, so when there's novel information, users are more likely to respond. And when there's positive reciprocity, users are more likely to respond. So including that information, we construct models with just recency and the interaction of the factors. And we find that when we have the interaction of the factors, the models are better performing, that they fit the responsiveness data better. So the insights are that under information overload, users tend to focus on what they most recently received in terms of response, and that conversations by globally popular users are probably deprioritized, which is also confirmed in some of the existing analytical literature. And there's a slight tendency to prioritize new information or information that's unfamiliar to the user, and a slight tendency to prioritize reciprocal relationships. So if you replied to that person in the past, you'd probably reply to them again. So to conclude, evolutionary model discovery has helped us address 4 challenges in my opinion. So it's helped us solve the fact that you'd have to, in order to do this sort of rule exploration, you'd have to do this repeated manual implementation, which can lead us into programming error. So genetic programming helps us solve this. And the fact that if you did do this sort of repeated manual implementation, such as suggested in pattern-oriented modeling, then there would be no standard structure, representation structure, to compare factors across the models that you've developed. And that's fixed by having a fixed tree representation in the form of the genetic program syntax tree. And there's been limited implementation support. There's been, as far as I know, not much support for genetic programming of agent-based models. And this open source Python library helps us, gives us the software required to do this. And basically, we're trying to bridge the disconnect between theory and data here by respecting the fact that agent-based models are typically conceptualized with social theories in mind. And the conclusion of the case studies, the ancestral Pueblo probably considered soil quality, social presence, and distancing in their farm selection behavior. Mixed patterns of segregation are more likely to occur with racial preference, avoidance of crowding, and resistance to move. And response prioritization on social media under information overload happens according to recency, and where conversations by globally unpopular individuals are received with novel information. Yeah. Thank you very much. Any questions? Josh?
I think it's just spectacular work, as you know. But so congratulations, and on the dissertation.
Thank you.
So I think it's wonderful, state of the art, really.
Thank you.
If you want to go back to any of your lists of utility functions for the segregation, for example,
okay.
This is just that graph in particular is what I had in mind.
This one?
That one, yeah.
Yeah.
Where I said, we may not be able to say, metrize the space of utility functions, and it may not be necessary to. I mean, here you've got, I don't know how many that is, several, many competitors, all of which do very well in generating the phenomenon. So it seems to me, if you say, here is a family of utility functions, all of which have high generative power, that is robust. I mean, it seems to me you're saying, here we've got our teeth into the phenomenon. Here are the factors. They can have different weights, different combinations. But you're saying what really matters, what's really driving it. These are the factors that matter, and here are several of the ways in which they could be combined to generate the phenomenon. So I think that's a huge advance over a singleton rule, where people can say, yeah, well, you found that rule, and now there must be many others, and so forth. And here you're saying, yep, there are a bunch of others. Take your pick. They all have high generative power, and we therefore believe that these are the main factors at work in producing this social phenomenon. I think that's just great.
I'm not sure I would call it robust.
Well, okay, we could argue about that.
Diverse.
Diverse, fine, sure.
But robustness would be that you saw consistent use of various parameters.
I agree with you, man. Let me just mention one thing too. Because the people in the room know a lot more about economics than I do, but the main issue that someone like, say, a hardcore competition would say is that there are now, for example, on many of these, there are 4 parameters implicit here, right? There's a 1 and a 2 and a 4, whatever, right? And so now you have the issue of possibly being badly overfit, right? And so as science, it's obviously a better fit, but it's not obviously a better science.
Yeah, if we look just at the most optimal optimal trees or functions that we receive, like I said before, sometimes it's hard to find a global optima, and I think the value of it lies in that factor importance of how these certain factors are repeatedly occurring in the best performing simulations. I think that's where the value lies.
But the argument is that's not what you're saying. I think what I'm hearing you say is still fit. Yeah, there's too many parameters. Yeah, and so if I give you a whole bunch of parameters, a pick which one's going to fit your data, you're going to find a primary one, you're going to find some more, and you'll get better fit. But I think which brings to mind when I saw your later slides, your later slides had, I think they were C indexes. There were C indexes underneath, C indices underneath them? Yeah, here.
This one?
So it's the order of magnitude on the C index, and I'm not sure what that means, but there's a huge change between 0.0073 and 0.01, and then you're getting into the 0.3, right?
Yeah.
So I'm not sure how to interpret that, but and I'm not sure whether all that extra C index is just coming from overfitting your data.
Yeah.
And if I gave you a bunch of other parameters, you'd find some way to put them together too. I mean, it is comforting that you're finding the same ones over and over, but I'm not sure. That's the thing. He has a bunch of other parameters in there. And it picks these ones instead. It doesn't fit.
They typically don't fit the data.
It's over, but it's sort of it's a varying size dimensionality that you're giving the system, right? You're saying I'll give you 10 parameters, I'll give you 9 parameters, 8, 7, and it's picking 4, but it's still picking 4.
And I'd also like to suggest, go back to the table with all the different parameters in there. One other seems to me one other aspect of it, which is probably solvable, but at the moment is not solved, is that all of the agents have the same behavior specification. In reality, they're going to be very heterogeneous. So this may just be picking up the fact that there's heterogeneity present.
Right. Yeah.
But now it's ceteris paribus, means all those computed C indices are ceteris paribus on everybody being homogeneous.
Yes, that's a very good point actually, because probably things like this, so where the tolerance diversity is best negative and positive, that sort of hints to me that there is a need for heterogeneity for better solutions. So yeah, I agree with that. But so the homogeneity, if it does exist in these models, are because of the parameters. So some of these parameters produce distributions and the agents are aligned across these distributions sometimes. So in the segregation model, we have tolerance distributions where agents are either allocated to high tolerance or low tolerance. So they are heterogeneous in that aspect. But in the behavior aspect, yes, there's room for improvement there.
I would just say that in the original Schelling model, they're all homogeneous too, and I think maybe subliminally you were thinking stay with that picture.
Yeah. So it's a step forward. Yeah.
Generate just Schelling.
Then it's solution the whole population.
Right, exactly.
So it's the whole population.
And then as a
Another comment that sort of goes with this review a little bit. We don't want to revigorate the notion of Occam's razor in that worrying about overfitting. The thing that's interesting about this relative to the original Schelling is the Schelling result was horrible. That is, we don't like it, but it also is sort of implausible because it leaves things out that we know are important. This shows that the concept that there are interactions among these variables, ones that we intuitively believe ought to interact, that's really an advance. The fact that you could assume a sort of simple-minded rule and fit data, that isn't very interesting. But when you put all the factors together that people think are interesting and they interact in interesting ways and also reproduce the data, I think that's a big improvement in science relative to we got a really good fit with one stupid parameter.
So I buy that, Paul, but I'm gonna be able to use Tom's own words here. And so listen. So there's a 1978 paper by Vandell and Harrison, and the interesting thing about the paper is that the obvious lacuna in Schelling's work is that there's no prices, right? There are no housing prices are going to be homogeneous. Right? You can move anywhere. So what Vandell and Harrison did is they put in a whole bunch of stuff that economists would think should matter, right? And of course they can get things that are slightly somewhat better fit. And Tom's response was, what? You can probably guess. That's not the point of his model. Right. The point of his model was something quite different. It was the qualitative idea that you could get. And so now the question is, does Tom's main point depend on having those additional factors in there or not? And I think that Tom would probably say, is that it does not matter.
Well, he would have said, I don't, of course, he would have said, but I'm sure he would have said, look, I didn't posit that as a serious empirical model of actual racial segregation anywhere. It was an example of micro-motives, macro phenomena, and so forth. Very, very beautiful one, but provocative.
Empirical ones since then, but which are not illuminating the Tom.
Right, exactly right. He has the beautiful general result, and, here we're defending Tom.
I think.
I think that's...
Just for the record, the Vandell and Harrison paper, we read that when the Sugarscape model was finished, and it was that was the first time we heard of the Schelling model. Neither of us knew about it when we built the Sugarscape thing. So you always
the Tom has to be sitting.
It's funny because I've heard people describe Sugarscape as an extension.
I know.
Of the Schelling model.
And then in an abundance of scholarly courtesy, they credited him with being prescient. And he was, and it's a great model that came before our model, but it had nothing to do with our model. We didn't extend Schelling's model. After the fact, we learned about it and decided, this is cool to implement, and Robbie did a cool job on that. And
we brought Tom in.
And we brought Tom in,
And if you comment here, if you can show me the utility function.
Yeah.
It's not completely random if you look at the process, because we have to remember always to go back and give interpretation of what we see. Because if there's an interpretation, maybe it makes sense. If there's no interpretation, it's garbage. It's not completely garbage. It's not perfect. But
this one?
Utility function?
Yeah, these ones.
So erase, of course, is important. F move is very interesting. It's negative because it means that if you would like to have neighborhoods which are integrated and segregated, some people have to stay longer. It means that they cannot move away. It means they're either poor. So the machines try to create economics without having it. Like they couldn't move, they don't nobody to go, no money. Minus move is money, by the way. Isolation, I'm not sure, by the way. It's not really, by the way, if I can be a critic, isolation, I'm not sure if it's an urban, you can isolate in urban areas because you can't create any park, density is high. But the first two make sense completely. And actually, minus move, it means that some people cannot move away, they stay, even if they're unhappy. and because they're stuck, and they are poor people. So it's very interesting that we got quite a reasonable result here.
Thank you.
I had one other silly Josh personal note. When we for I don't know how much, for 20 years, I didn't want to conclude and make this point about Tom being pretty much irrelevant to our work. And then after 20 years of friendship and collegiality, we had this conference at Rob's on the 20th anniversary of the Sugarscape, and we invited Tom. And it was at that occasion that I was going to say that, look, despite our affection and long collegiality, the thing really had nothing to do with our Sugarscape. And it was a real act of courage, and he died before he showed up. So that was just another, anyway, I say,
Well, I did an interview with him as part of the agent-based modeling course. It's up online. I think it might have been the last interview he gave before he passed. But in that interview, it was interesting because I had a lot of conversations with him about agent-based modeling, and I asked him and he was kind of like, the impression I got from talking with him was that he enjoyed being called this person who was known as having created agent-based modeling, but he didn't really think anything he did had anything to do with the field, right? That was the impression that he gave out several times during it. He was much, much more interested in talking about his contract work and stuff like that he wound up getting the Nobel Prize for than he was in anything having to do with this sub part of the field. So I think he would have been, at least in the conversation I had with him, I think he would have been fine with that, yeah.
So that's absolutely true, but the man had, as Paul knows, he was at the ramp for a while, and he had very strong modeling ideas. He had a very strong sense of what a model should be. And so I'm just going to report that, since Josh mentioned a vignette, I'll mention one vignette too. So on the day the Sugarscape book came out, at Brookings we had a media event, okay? And we had invited Tom to be on the panel or something. We invited Tom, Simon, et cetera. But it turns out that we hadn't gotten a response. So we had some people up there were discussing. So there's a Q&A section, and there's one Scientific American reporter who none of us got along well with, Horgan.
I don't know.
Yeah.
He stood up and he asked a question. He goes, "You guys have shown us some stuff, but can I get anything to happen in your model? Can't anything, everything possible can happen, whatever. It's not really science, is it?" And that was his big thing, right? Is it science or not, right? And before Josh and I, we look at each other and we're trying to figure out how to respond to this question, right? And before we can say anything, Schelling pops up from the back of the room. We didn't even know he was there. Schelling pops up, and he answers. He takes on Horgan right there himself, and he says in his kind of New England accent there, he says a model is done, not when nothing else can be added to it. Yeah. A model is done when nothing else can be taken away from it, and you get the results you want. Yeah. And Horgan basically just sat down. He didn't know what to say to that. And so even though Tom was not a computational person anyway, but he certainly has strong modeling ideas. Yeah. I will say though that one thing I've discovered in the last couple of years is that, and this is documented in a recent JAS paper by Hegselman, is that there is in fact a long history of kind of unpublished or buried manuscripts in the Schelling case. And so there is this incredible paper, which if you can't find it, I can get it to you. It's called. So Schelling wrote a paper in something like 72 or 73, where he had been quite dismissive of computing. So actually, John Cassidy at Rand had written the model for him. Yeah. But when Tom got back to the Kennedy School, there probably wasn't Kennedy School at the time, he had somebody help him. And so there is a paper called "How the Computer Can Help with the Work," and that's the actual title of the paper. And it's Tom's reportage on how there might be some advantage to doing things in an automatic form.
Yeah, that's in that discussion. A little of that discussion's in the interview I did with him as well, because he mentions that he did not have the ability to program this, and so he worked with this guy for, I don't know who it was.
There was some guy who basically was going to be a PhD scholar, went off to the diplomatic corps.
And he taught Schelling how to program, essentially.
Yeah. Anyway, our homage to Tom in this connection and this clarification is in the video of my keynote talk at Rob and my event. So, but not to, we both thought very highly of Tom, and he was very shaped our work in other ways, and we had lots of feedback from him on subsequent novels and so on. So, not to diminish its greatness or value to us.
So getting back to this though, how big were your population?
So they varied. For the Anasazi, it's a variable population.
Well, so how, yeah, for this one.
In this one, so,
And is everyone in the population using that one? They're not, right?
sorry?
Not everyone in the population is using that rule.
Yes, they are.
Okay.
Yeah, everyone in the population is using that rule.
But when you run it multiple times, you get these.
Yeah. The density parameter is probably the more important one here. And in these diagrams, you see a density of 0.75, but in the total exploration, I used a variable density between 0.5 to 0.95. Yeah. Here you see 0.75. Yeah. Yeah. So in each of these evolution model discovery genetic programming runs, the parameters of the model are initialized randomly so as to reduce bias. So we don't have to calibrate after we have the models anymore. Yeah.
This might be a good time to transition since I'm next.